Picture two objects floating alone in space, light years from any star. One of them is a planet. The other is a star that never quite got big enough to shine. Now try to tell them apart just by looking. That is not a trick question. It is one of the strangest open problems in modern astronomy, and an object 620 light years away just forced scientists to confront it head-on. Have you ever wondered where the line actually gets drawn between a planet and a star? Stars form when a huge cloud of gas collapses under its own gravity, until the core gets hot and dense enough to ignite nuclear fusion. Planets form differently, usually inside a disk of leftover material orbiting a young star. But there is a gray zone in between. Objects with somewhere between about 13 and 80 times the mass of Jupiter are called brown dwarfs. They are too small to sustain the fusion that powers a star like our Sun, but too big to be considered ordinary planets. Below 13 Jupiter masses, things get even stranger. That is roughly the point where an object can no longer fuse deuterium, a heavier form of hydrogen, at all. And yet astronomers keep finding objects below that threshold floating completely alone, with no star to orbit and no planetary system to belong to. Scientists call them free-floating planetary-mass objects, or rogue planets if you want the more dramatic name. The first ones were spotted in star-forming regions back in 2000, and they immediately raised an uncomfortable question. Are these the smallest, faintest things that can form the exact same way a star does, just from a cloud too small to ever ignite? Or are they full-grown giant planets that formed around a star and then got violently thrown out of their own solar system? Nobody has settled that argument yet. And it matters, because the answer changes how we think about what a planet even is. One of the best ways to investigate is to look at what surrounds these lonely objects. Many of them turn out to have their own disk of gas and dust circling them, just like a young star does. That disk is a clue. If a starless, planet-sized object still has a disk and is still actively pulling material from that disk onto itself, it is doing something that looks a lot like how baby stars grow. That process is called accretion, and it might be the single best tool astronomers have for figuring out whether these objects grew up like stars. To understand why accretion is such a big deal, it helps to look at what it does in ordinary young stars first. A newborn star does not grow at a smooth, steady rate. It tends to feed in fits and starts, sometimes staying quiet for years, and then suddenly gorging on huge amounts of gas in a matter of weeks. Astronomers have names for these feeding frenzies. The most dramatic ones are called FU or bursts, after the prototype star FU Orionis, and they can make a young star flare up by 5 magnitudes or more, staying bright for decades. A smaller, shorter version is called an EXOR burst, named after the star EX Lupi. In 2008, EX Lupi brightened dramatically for about 7 months, with its accretion rate jumping by a factor of around 30. So why does this happen at all? Why would a young star or a young planet-sized object sit quietly for years and then suddenly binge? The leading explanation involves instability in the disk itself. Material can pile up in the inner disk instead of flowing smoothly inward, until something, possibly a magnetic or gravitational trigger, releases it all at once in a rush toward the surface. That inward rush often gets funneled by magnetic fields, guided along invisible field lines like water down a drain, and it slams into the surface at specific hot spots rather than spreading evenly. Astronomers can actually see the fingerprint of that funneling in an object light spectrum. When gas crashes into a hot spot, it produces a very specific, lopsided signature in certain spectral lines. This kind of magnetically channeled accretion has been documented in young stars and brown dwarfs for decades. What nobody had confirmed was whether it could also happen in something with barely more mass than a large planet. None of this would have been possible without incredibly sensitive infrared instruments. Objects this small and this cold are almost invisible in ordinary visible light, which is part of why free-floating planetary mass objects went undiscovered for so long. That brings us back to the lonely, starless object 620 light-years away, in the constellation Chamaeleon. Astronomers call it CHA 1117-7626. Its estimated mass is somewhere between 5 and 10 times that of Jupiter, which puts it squarely in planetary territory, not stellar. It has long been one of the best-known examples of a free-floating object with a disk and ongoing accretion, which is exactly why a team of astronomers kept a close eye on it. In 2025, that attention paid off in a way nobody expected. A team led by astronomer Victor Almendros-Abad used the X-shooter spectrograph on the European Southern Observatory, very large telescope in Chile, combined with instruments aboard the James Webb Space Telescope, to track this object across 5 separate observing sessions between April and August of 2025. The first 2 rounds of observations in April and May showed the object in a fairly ordinary, quiet state, similar to what had been seen before. Then by late June, everything changed. Have you ever seen something so unexpected in the data that the whole team had to double-check the instruments? The emission lines connected to accretion, the signature of gas actively falling onto the object, suddenly and dramatically strengthened. And they stayed strong through July and all the way into August, the last month the team was able to observe it. So just how much did things change? The numbers are what make this genuinely remarkable. Comparing the quiet months to the active ones, the team measured a 6 to 8-fold increase in the object mass accretion rate. That is the highest accretion rate ever measured for anything in the planetary-mass range, full stop. During the burst, the object also brightened by roughly 1.5 to 2 magnitudes in visible light. Its optical brightness climbed by a factor of 3 to 6 compared to its quiet state. Even in the mid-infrared, where the disk itself glows from heat, brightness rose by 10 to 20%, most noticeably at wavelengths tied to the inner, hottest part of the disk. But the most striking evidence came from a single spectral line, hydrogen alpha. During the burst, that line split into a double peak, with one side shifted slightly toward the red, meaning gas moving away from us. That specific double-peaked, red-shifted shape is the same signature astronomers see in young stars undergoing magnetically channeled accretion, cool gas falling inward along field lines and slamming into a hot spot on the surface. A remarkably similar profile change was seen back in 2005 in an accreting brown dwarf called TWA-27. Seeing it again here, in something with barely more mass than a handful of Jupiters, suggests the same magnetic machinery that feeds infant stars can also operate at planetary scales. The disk chemistry told its own story too. Using the James Webb Space Telescope infrared instruments, the team detected a brand new emission feature consistent with water vapor, something that was completely absent when the object was quiet. They also saw real changes in the hydrocarbon emission lines already known from this disk, the same chemical signature that marks it as unusually carbon-rich compared to typical planet-forming disks. It is the first time anyone has documented an accretion burst actually reshaping the chemistry of a disk around an object this small. One thing barely budged, though. The disk silicate feature, tied to the mix of dust grains close to the object, looked almost identical before and during the burst, which tells the team the burst mostly heated and rearranged gas, not the deeper dust structure. Now, does any of this prove CHA 1107-7626 is basically a miniature star? Not quite, and the researchers are careful about that distinction. The actual accretion rate they report depends heavily on which physical model gets used to translate a spectral line brightness into an actual mass flow. 2 different modeling approaches used in the study agree closely on how much the accretion rate increased, but they disagree by roughly a factor of 10 on the absolute amount of material being swallowed at any given moment. That is a useful reminder. Turning a spectrum into a real physical number always carries genuine uncertainty, even when the underlying trend is rock solid. There is another twist. An older spectrum of this same object, taken back in 2016, hints that it may have gone through a similar episode once before. If that is true, this would not be a one-time fluke. It would be a recurring event. But with only 2 data points a whole decade apart, the team cannot yet say how often it happens, or exactly how long any single episode lasts. So did this discovery finally settle whether objects like this form the way stars do, or start out as planets that got kicked out of their home systems? Not on its own. That bigger question is still open. But this burst adds a genuinely new piece of evidence to the puzzle, the kind of evidence that only shows up if you happen to be watching at exactly the right moment. By the time the observing campaign wrapped up in August 2025, the burst was still going. That means it had already lasted at least 2 months, with no clear end in sight when the team last checked. What is already certain is this: CHA 1107-7626 has become the first object in the Planetary-Mass range confirmed to go through the kind of large, long-lived outburst astronomers call an EZOR event, a category that, until now, had only ever been seen in young stars. Every giant planet in our own solar system, including Jupiter itself, went through some kind of early growth phase billions of years ago. Watching a planetary mass object accrete in real time, even a starless one, is about as close as astronomers can get to rewinding the tape on how gas giants actually come together. A world with no star of its own, feeding like a newborn one. Somewhere out there, the boundary between planet and star just got a little blurrier.